Your lecturer is Professor Jeffrey C. Grossman. Dr. Grossman is a professor in the Department of Materials Science and Engineering at the Massachusetts Institute of Technology. Recognized for his cutting-edge research and innovative interdisciplinary teaching methods, Professor Grossman has appeared on PBS and the Discovery Channel's Science Channel. His current research focuses on developing energy sources for the future.
Hello, and welcome to our first lecture on thermodynamics. In this lecture, I hope to share with you my excitement and passion for this topic, and to convey to you why the subject of thermodynamics is so crucial. I started out studying theoretical physics, and I got both my bachelor's and PhD degrees in that subject. Now, I'm a materials scientist and engineer, and for me, it's the connection of fundamental understanding to actual working, relevant devices and technologies that strikes at the heart of my passion. What drives my work is the connection between the science of materials and the technology those materials can influence. And that is what the discipline of materials science and engineering is. It is, at its core, the study of what makes a material behave the way it does. What's under the hood of a given material? And once I know that, how can I engineer it to be something better or to do something different? And I'm excited to teach you this course because it's always some aspect of thermodynamics that is in fact under that hood. I'm going to be sure to get across the excitement of real problems that we can interact with and see that relate the key concepts directly to experiments. To accomplish this, this course will be demo-driven, meaning that in nearly every lecture, at some point or another, I'll take a break, put on my lab coat and goggles, and go and smash, break, light on fire, or otherwise convert energy from one form into another. I'll pour water into a bowl that looks just like regular water, but becomes ice as soon as it hits the bowl. I'll light a $100 bill on fire without it charring a single bit. I'll break the bottom of a glass bottle cleanly off by striking it at the top. And I'll boil water by cooling it instead of heating it. I'll show you what is perhaps the world's simplest motor, involving a battery, a magnet, and a single wire. And I'll give many other examples of mechanical work. We'll light a piece of cotton on fire using a hammer and the laws of the ideal gas. And I'll show you how to make a balloon not pop, even when you light it on fire. I'll demonstrate that matter can exist in all three phases at the same time: gas, liquid, and solid. We'll run all sorts of engines, from ones you may know about already that run on heat to ones that are less common, like those that run on surface tension or none other than entropy itself. And of course, this list wouldn't be complete if I didn't tell you that I'll also use a very simple chemical reaction to create a massive 10-foot-high eruption. Consider the following question. You've probably heard of the periodic table of the elements. 118 of them exist officially, but there are around 100 elements that are stable and found naturally. So, how many of those 100 elements do you think there are in your cell phone? It's quite remarkable to think about. My cell phone has 64 different elements in it. How did we do that? How do we take around 2/3 of all of the known stable elements and make them perform all of the different functions that a cell phone does? We literally dug up chunks of the Earth's crust, extracted out this broad range of elements, and then processed them in a whole bunch of particular ways. And voila, I can shoot a high-definition video and text it anywhere on the globe, check sports scores, the weather, or movie times, listen to millions of songs, or simply make a phone call. All because I figured out how to coax those 64 different elements into just the right positions and combinations. But how is this actually done? It has to do with the way materials interact with each other and how they respond to processing conditions. If you've ever cooked a meal, then you know what I'm talking about. Let's think of the elements in my cell phone as the ingredients we're using to cook with. The processing conditions for those chocolate chip cookies might be a temperature of 375 degrees Fahrenheit and a time of 10 minutes. But for the brownies, it's a temperature of 300 degrees Fahrenheit and 45 minutes of cook time. And the oven is not under any extra pressure, so those are both examples of cooking at the same pressure as the rest of the kitchen. But if you've ever used a pressure cooker, then you know that pressure is another way to change the processing conditions. And just like temperature, changing the pressure makes a big difference. So we have some initial set of raw materials: the flour, vanilla extract, eggs, sugar, and so on. And when we mix them together in just the right proportions and then process them under just the right conditions, then we can achieve a certain desired outcome. It's the same thing with elements and material science and engineering. We start with our initial ingredients, which correspond to the elements of the periodic table. We process them in just the right ways, and we get a material that has just the right properties for some desired application. At the heart of this example is the fundamental nature of energy and all of its forms. I put mechanical energy into the eggs when I beat them. Chemical energy is rearranged when sugar is dissolved. And heat energy is inserted when the food is baked. One of the key questions you're answering when you cook a meal is, how does energy in all of its different forms change the nature of a material? And how can we understand these energy flows so that we can control them to make materials take on certain properties or behave in a certain way? Taking this a bit further, how can we become master chefs of not just food, but of all known elements? This, in essence, is the topic of thermodynamics, and it's absolutely essential in science and technology. And thermodynamics is not just a foundational topic for material science and engineering. It's also at the core of many other disciplines, like chemical and mechanical engineering, or biology and chemistry, and physics. Each discipline may take a different view of thermodynamics, some emphasizing more how it applies to engines, while others delving more into the theoretical, statistical nature of the subject. But in the end, they all place this topic at the top of their academic food chain. And it's for very good reason. As Einstein famously said about thermodynamics, it is the only physical theory of universal content that, within the framework of applicability of its basic concepts, will never be overthrown. Now, that's a powerful statement, given that he had literally just overthrown the laws of classical physics by helping to develop the quantum theory. Thermodynamics is a subject that connects deep and fundamental insights from the atomic scale of the world all the way to the highly applied. And it's a topic that has been pivotal for the technologies that have completely revolutionized the world as we know it over the past 500 years. And perhaps the single most important differentiator for this subject, and the aspect that makes thermodynamics so incredibly important to my own research in energy, is that very word, thermo itself. It's the fundamental understanding of heat and temperature, and ultimately entropy, that separates this subject from all others. Thermodynamics means literally heat in motion. And without an understanding of heat, our ability to make science practical is extremely limited. Heat is, of course, everywhere. And putting heat into motion, well, that alone is at the core of the Industrial Revolution and the beginning of our modern age. The transformation of energy of all forms into and from heat is at the core of the energy revolution, and fundamentally what makes human civilization thrive today. So, in answer to the question of why thermodynamics is such a pivotal topic, let's pose another question. What if we had to start all over? What if the buildings were leveled, the cars and roads were gone, hospitals disappeared, and electricity was only found in lightning strikes. Basically, what if nothing were here? How would we rebuild our world? What would the challenges be? What tools would we need? What knowledge would we need? The place to start, in order to answer such a question, is to ask what the variables are in the first place. What are the givens? That is, what are the things that we know about, the things that we have? What are the things that we may not have but need to know about? These are the variables. And as you can imagine, these would be the ingredients at our disposal, as well as what our kitchen can do. In the example of cooking a meal, it would come down to different plants and animals and different ways to process those ingredients. In our effort to rebuild the world, we make this more general. We ask what raw materials we could find, plus the different forms of energy we would be able to harness to manipulate those ingredients. These energies could include heat, or mechanical forces, or chemical reactions as examples. And once we knew what the variables were, next we'd need to know how those variables interact with one another. In other words, how do materials respond to their environment? How does one form of energy change when another form of energy is introduced? What is the interplay between energy of all forms and matter? The answers to these questions can be found in thermodynamics. Thermodynamics is the subject that holds the key to understanding how energy in all of its forms, including heat, changes the nature of the materials that make up the world. Without understanding these relationships, we could not rebuild our world. We would not be able to make an engine that turns heat into mechanical work. We would not be able to make electricity from spinning turbines, and then use that electricity to perform useful tasks, like produce light or communicate across great distances. We would have no understanding of what ingredients to mix in what proportions and at what temperatures to make steel strong enough to build buildings and airplanes. And we would certainly not be able to make those airplanes fly. How would we begin? Well, first, we need to get a sense of what the variables are that we can control. I mentioned a few already, but let's list them all together here. There would be temperature and pressure, since I could make fire to control heat, and squeezing or banging on a material applies a force or pressure to it. I could also control the volume or mass of a substance simply by changing the amount. And I can think about controlling, at least in some cases, the phase of the material. This means working with the material as a gas, liquid, or a solid, which, as you probably already know, is going to be a function of the temperature. And then there would be the chemistry itself, which goes back to those raw ingredients and how I mix different relative amounts together. Then I'd start varying the properties with respect to one another to see what happens. I'd try to vary just a few variables at a time while holding as many of the other ones fixed. For example, I'd change the temperature and see if the volume changes, or hold the temperature fixed and add more material and see if the pressure changes, and so on. And this is exactly what scientists and engineers did to lay the foundations of thermodynamics. And it's what we'll do in the early lectures of this course. We'll develop a strong sense for each of these crucial variables, and we'll learn the relationships between them. We'll build our knowledge, starting with the properties of materials when they're in a single phase, like a gas. And then we'll learn how and why materials can change phase as a function of their environment. And since heat is one of the single most important kinds of energy, we'll begin our course in the very next lecture with the way in which thermal energy is measured. That would be temperature. But just knowing the variables is not enough to build something useful. It would be like knowing all of the ingredients in a chocolate chip cookie recipe, but not knowing how much of each one to use or how to cook them. And even more importantly, we'd have to figure out how one cooking process is related to another. Would I achieve the same results by baking in an oven, frying on a pan, or boiling in water? That's why Once we have a solid understanding of the different variables of thermodynamics, we'll move on to learn about the laws that bind them all together. The first law of thermodynamics is a statement of conservation of energy, and it covers all of the different forms of energy possible, including thermal energy. At that stage of our knowledge, needed in our attempt to rebuild the world, we would have a fantastic grasp of the different ways in which energy can flow into or out of a material. By taking a look under the hood of materials and peering across vast length and timescales, we'll learn that at the fundamental level, for the energy stored in the material itself, all energy flows are equivalent. We'd see that performing work, like say applying a pressure or initiating a reaction, is entirely equivalent to adding heat. This is one of the fundamental pillars of thermodynamics, and it's captured in the first law. And armed with that knowledge, we would learn that there are many ways to manipulate the properties of materials, and that we can adapt our processing techniques to whatever is most convenient given the tools we have on hand. We would also be able to experiment with the trading back and forth between heat and work. We'd see that vast amounts of heat can be generated not just by lighting fire, but also by other means like the friction of two pieces of metal rubbing together. As chefs, we're learning that there are more ways to process our ingredients than we might have originally thought. And by playing with the relationships between those basic variables, pressure, temperature, volume, and mass, we'd start to figure out how to make heat go the other way and convert into some form of useful work. For example, taking advantage of the fact that heat makes a gas expand, which in turn can be used to push on a piston, we'd be able to make our very first engine. Now, at this point, in terms of our rebuilding process, we could do a whole lot. We'd be able to make an efficient form of concrete that pours easily and dries quickly, since we'd have learned what temperatures are needed to make the calcium silicate particles of just the right composition and size. We'd probably have figured out that the properties of steel depend very closely not just on how much carbon is added to iron, but also on how rapidly the molten metal is cooled into a solid. We'd then be able to take advantage of that knowledge to make the different types of steels needed, whether for buildings, railroad tracks, or plumbing pipes. And we'd be making some of our very first combustion engines, turning the heat from fire into mechanical motion. In short, with the topics of thermodynamics I've described to you so far, we'd be able to re-enter the Industrial Revolution. And yet, it would be hard to move past this point. Yes, we've put back some of the basic building blocks of the world, but there would still remain enormous gaps, like the ability to make and control many more kinds of materials, like plastics, or the development of modern medicine, or the ability to create highly tailored chemistries, or for that matter, the entire information technology revolution, to name just a few examples. You see, in terms of the knowledge we'd need, we would have a thorough sense of the different driving forces in nature and how to control them to change the variables we care about. Put energy into a system, and that system will respond. This is the nature of a thermodynamic driving force. It's a way to push or pull on a material with any type of energy. Apply a pressure and see the volume change. Increase the temperature and watch a material melt. A force is applied and a response is observed. But the driving force and corresponding response alone do not tell the whole story. For that, we need something else. We need to know what it is that governs when and why the system stops being driven. In other words, we need to understand why a system comes to equilibrium. This means that given any set of external conditions, like temperature, pressure, and volume, on average, the system no longer undergoes any changes. This concept of equilibrium is so important in thermodynamics that I'll spend a good amount of time discussing it in the early lectures of the course. But it's not until our lecture on entropy and the second law of thermodynamics that we find the missing knowledge I just described. Consider an analogy of a ball rolling down a track. If the track points down, then we know the ball will experience a driving force, due to gravity in this case, to go down the track. So that's the driving force and the response. But we still have the crucial question of where the ball will come to rest. Of course, we have an intuitive sense here that it will stop where there's some sort of minimum point in the track. At that point, the ball might go back and forth for a while, but if there's a little friction so it loses a little energy as it goes, eventually it'll come to rest there. That's the equilibrium point. The second law of thermodynamics allows us to understand and predict this minimum point for any set of processes involving any type of energy transfer, including thermal energy. By combining the first and second laws of thermodynamics, we can predict the equilibrium point for a system under any conditions. That's pretty powerful stuff. And the thing is that, at least at first, it's not as intuitive as a simple ball rolling on a track example. That's because there are a whole lot more possible forms of energy that may be present than just gravitational energy. For example, there's the mechanical energy, which I already mentioned, and it's due to pressure times a change in volume. But there's chemical energy, which can lead to changes in the material composition itself. And many other forms, like energy due to magnetism, surface tension, and electric fields, to name just a few. So the track of thermodynamics can get pretty complicated. But there's one particular kind of energy that leads to the biggest departure from an intuitive picture, and that would be thermal energy. Thermodynamics is the subject that treats this energy on an equal footing with all of the other terms. And the reason it's able to do so has to do with another variable called entropy. We'll be talking a lot about entropy throughout this course because it's of absolutely fundamental importance to our subject. Entropy gives us the crucial link between temperature and thermal energy. It's a way to quantify how many different ways there are to distribute energy. And as we'll see, it's the foundation for the second law of thermodynamics. By understanding entropy, we will learn how to determine when and why a system reaches equilibrium. We'll gain an intuitive sense for the connectedness of thermal energy to all other forms of energy. And we'll understand why a perpetual motion machine can never exist. Entropy gives us nothing less than the arrow of time, since it's a thermodynamic variable that provides a means to predict which direction all processes will occur. It tells us how to find where the minimum of the track is, not just for a ball and gravity, but for any set of materials in any kind of energy terms. So, armed with entropy and the second law, we'll have filled the knowledge gap we needed to tackle the next step in our effort to rebuild the world. We'll be able to gain a deeper understanding of how materials both hold on to thermal energy as well as how they respond to it, something that we'll discuss in our lectures on heat capacity and thermal expansion. Our attempt to rebuild the world will involve a constant transformation of energy, and heat will always be in the mix during these transformations. And what we'll need to do with this energy very often is to create order from disorder. We'll make a car move by blowing up little carbonaceous molecules in an engine. We'll make chemicals pure from their raw, mixed up natural sources. We'll make computer chips out of sand and turn limestone into liquid to make roads and houses. Our bodies themselves are continuously taking energy from food to maintain ordered arrangements of trillions of cells, and we would begin to understand these processes more deeply. At this stage, we'll understand why it takes energy to create order, and why things don't just sometimes become ordered on their own. The concept of entropy answers these questions, as it provides a crucial bridge between heat and temperature. And as we'll see, unlike energy, entropy is not conserved. And yet, it does play a key role in energy conservation, since entropy allows us to bring heat into our fundamental equation for energy. We will tightly connect the first and second laws together to make the most use of our thermodynamic understanding as we rebuild. And by doing so, we'll be in a position to create maps of materials. Maps that tell us precisely what a material will do for any given set of conditions. These maps are called phase diagrams, and they represent one of the single most important outcomes of thermodynamics. They can be constructed from the knowledge of the first and second laws for any material. With phase diagrams, we unlock the behavior of a given material or mixture of materials in a manner that lets us dial in just the right processing conditions to achieve just the right behavior. With this type of control, we can begin making again the materials needed for electronics. We can dictate precisely when reactions will happen and in which direction, allowing us to make many more materials, as well as control over chemistry accurate enough to lead to modern biotechnology and medicine. With phase diagrams, we're able to make lighter machines, more efficient engines, myriad new materials, and completely new ways to convert and store energy itself. Because of how important they are, we'll spend 5 whole lectures to fully cover phase diagrams. And after that, we'll talk about a number of practical examples of how the knowledge of thermodynamics leads to crucial technologies. We'll fill in the gaps and learn key elements that it would take to put the world back. Fundamentally, at the core of this subject is the knowledge of what makes a material behave the way it does under any circumstances. And along the way, as we gain this core knowledge of thermodynamics, we'll see countless examples of how it impacts our lives. Back to the analogy of cooking in the kitchen, we'll see why you might burn your mouth on the cheese rather than the crust of a piece of pizza. That's the heat capacity, and it tells us how and why materials can hold on to different amounts of heat. When we learn about phase transitions and latent heat, we'll see how much energy it takes to make a material transition from one phase, like a solid, into another, like a liquid. And we'll see why ice floats rather than sinks, and how pressure plays a role in determining what phase a material takes on. We'll learn why it's possible to both boil and freeze a liquid at exactly the same time. And we'll learn what governs the behavior of mixtures of materials. We'll learn about the limits of making heat do mechanical work, like in a car engine. And we'll also explore a number of other ways that materials can be used to make things move. We'll learn about electrochemistry and the basic principles of a battery. And we'll put to rest once and for all the question of whether a potato can really power a clock. And through it all, the underlying processes will involve some form of an energy transfer, either to, from, or within a given material, from one form to another and to another still. Thermodynamics is the subject that governs all possible forms of energy transfer and tells us how to predict the behavior of materials as a result of these energy ebbs and flows. Thermodynamics is crucially important to our understanding of the world, and it lies at the core of our understanding of materials. And yet, it's perhaps the least intuitive introductory subject of them all. When we see a ball bounce, or not, we immediately feel the physics concepts of gravity, or energy and momentum. But when we add a dash of salt into our soup, does the increase in the salt's configurational entropy, which is, after all, what makes it dissolve, does that come to us with the same intuition? The answer is, in my experience, that the same basic intuition is missing from thermodynamics. A number of textbooks and now many websites do a fantastic job at teaching the key concepts like entropy, temperature, heat, phases, the conversion of energy from one form into another, and the seemingly endless permutations of fundamental equations and possible thermodynamic work terms, and of course the 4 laws that form the basis of the theory of thermodynamics. Those are the ones Einstein said will never be overturned. But you see, all these concepts often become stuck in many students' minds as either only sets of mathematical operations or else ideas that only apply to highly contrived examples as opposed to real-life problems. The concepts of thermodynamics badly need to be brought to life. I want to bring thermodynamics to that same level as other subjects where intuition is more natural, to get you to feel that same kind of intuition for the key concepts, which at first can appear quite a bit more elusive. Entropy, I'm talking to you. Now, I don't plan to make this a course with a whole lot of derivations, but I won't shy away from the math either. To learn thermodynamics means learning some of the basic math as needed, so that you can go back and forth between the key concepts and the variables and relationships that represent them. It would be a disservice to the topic if I didn't get into some of the math in order to show you how the important relationships between thermodynamics can be quantified. That is, after all, what engineers would need to do to rebuild the world. But I will always strive for a balance, never getting too far away from the key conceptual pictures. I'll be giving many analogies and many comparisons along the way, and as much as possible, I'll ground our discussions in real problems. By the end of this course, you'll be a master chef of materials who possesses not just the recipes, but a deep understanding of why a recipe gives the results it does. You may not be able to combine 64 elements to make a cell phone, but you'll have the knowledge that it takes to see how such materials could be processed in just the right ways to do so. You'll learn about the most important variables and how they depend on one another. And you'll gain the knowledge of the laws of thermodynamics, 4 laws that govern the behavior of these variables. These are the 4 laws that move the universe. So, what are we waiting for? Let's get started.